The following is an example of the extended exponential growth and decay model. An oven is heating up where the rate of change of its temperature is proportional to the difference between its current and preset temperature. The initial temperature is 25 degrees Celsius and the preset temperature is 220 degrees Celsius. After 5 minutes, the oven's temperature is 100 degrees Celsius. Find the oven's temperature and its rate of change after 15 minutes. Now this differential equation here models this situation. So an oven is heating up where the rate of change of its temperature, that's dp dt, is proportional to, is equal to K, so you can think of K as the constant of variation, the difference between its current and preset temperature, that's P minus N. So P is the temperature of the oven at a particular point in time, or any point in time, and N is the preset temperature, and that's a constant, that's a fixed number. Now the equation that solves this differential equation is P equals N plus A multiplied by e to the power of KT. After all, if you differentiate this, you get this. So this is the equation that generates this differential equation. Now our first step is to determine N and A, or their values. Now P approaches N as T approaches infinity. So what this is saying is that the oven's temperature approaches the preset temperature, that's 220 degrees, that's what we set the oven to, as time goes on. So N, you can think of N as an endpoint, so N equals 220. Now to deal with the initial conditions. At time t equals 0, N plus A equals 25 degrees Celsius. Now we've determined N already, N is 220 degrees. This means that A equals negative 195 degrees. Hence we could write the formula as P equals 220 minus 195 multiplied by e to the power of KT. Our next step is to determine the growth constant K. So we need another piece of information to help us here. Now we know that after 5 minutes, the oven's temperature is 100 degrees Celsius. So this bit of information will help us determine the growth constant. So let's substitute T equals 5 and P equals 100 into the equation and solve for K. So subtracting 220 from both sides and dividing both sides by negative 195, we end up with 8 over 13 equals e to the power of 5k. Taking the log base e, or the natural log of both sides, we end up with ln of 8 over 13 equals 5k. Dividing both sides by 5, we have k equals 1 over 5 multiplied by ln of 8 over 13. Now I'm going to leave k in exact form. Some questions may ask you to round k to so many significant figures, but I'm just going to leave it like that for now. Now at t equals 15, because we're interested in the oven's temperature and its rate of change at the 15-minute mark, so at t equals 15, we're going to substitute t equals 15 into this equation, our exponential growth and decay equation. So P equals 220 minus 195 multiplied by e to the power of 15k. Now we have the value for k already. So evaluating this, we get P equals 174.556213 degrees Celsius, or roughly 175 degrees Celsius. And the rate of change of temperature with respect to time at that point is equal to K multiplied by 174.556213 minus 220, and we get dp dt equals 4.413 degrees Celsius per minute. Now this graph models this situation. Okay, so it's only a sketch, but we can see here that the oven starts off at 25 degrees. It's rising to try and reach 220 degrees, but it's in a way it's decaying, but in sort of decaying in a positive manner rather than decaying downward. It's actually decaying upwards. So this curve, even though it's rising, it's asymptotic to the 220 degree Celsius line, or this horizontal line.